G'day guys, and welcome back to another further 101 lesson. My name is Jake, and today we'll look at how numerical data can be displayed and analysed. This video forms part of the Univariate Data sub-series, which is part of the core module series on data analytics. As always, use the timestamps in the description below to navigate this video. But before we jump in, let's do a quick refresher on numerical variables. Now, a numerical variable contains data that indicates the quantity or value of what is being recorded or observed. Classic examples of numerical variables are a person's weight and shoe size, as well as a number of pets owned by a person. There are two subtypes of numerical variables under the umbrella term of numerical variable. If the numerical data is typically collected by counting how much there is of something, the variable is defined as discrete. A clear example is the number of siblings in a family. This data is usually fairly obvious, as the data values are almost always whole numbers, although there are some exceptions to this. If the numerical data is typically collected by measuring the value, the variable is defined as a continuous variable. Some examples include a person's height or weight, or their lap time in a swimming carnival. Now, much like categorical data, numerical data is usually organised into a frequency table. There are typically three sections to a frequency table for a single numerical variable, as represented by the columns. The first column lists the numerical intervals. You might have guessed that counting the number of times each unique data value occurs would be tedious and not very informative, and you would be right. To overcome this problem, categories are artificially created, defined by a uniform interval or number distance. For example, the table below has grouped the numerical variable number of goals kicked in a season into intervals of 5 goals, ranging from 0 goals to 25 goals. Typically, you are instructed on what interval size to use, otherwise you just choose the most appropriate interval. The second column is a tally of the numerical data that falls within each interval. Do note that this column is optional and often not displayed in the final exams. However, it is useful to complete a tally yourself if the data is listed individually in rows and not already organised into a frequency table. The final column provides the frequency of each interval. That is, it indicates how many data points are in each interval. Frequency can be in one of two forms. A count gives the actual number of numerical data points within each interval, whereas a percentage gives the percentage of total data values within each interval. Sometimes both the count and percentage are given, but usually only one is provided. That means you will be expected to convert an answer to the other frequency type if the question demands it. For example, you may be asked to provide the percentage of persons who kicked between 15 and 20 goals, even though the table only provides a count of these goal kickers. Avoid this costly mistake of skimming an answer and incorrectly assuming the frequency type required by double checking what frequency type is provided in the table and asking the question before answering. Complete a conversion from one frequency type to the other if needed. We will run through this conversion in a moment. But let's go back to the frequency table. At the bottom of the frequency table is a total row. This may not always be provided, however it is extremely important that you count the total of the frequency column, even if the total is provided in the question information. This not only allows you to check that you have completed the frequency table correctly, but it also provides valuable information that will almost certainly be used in the analysis. Do note that sometimes the total of a percentage frequency column may be a couple of decimal places off from the expected total of 100%. Typically it might be 99.9% or 100.1%. This is usually a rounding error, as the frequency percentages are typically only written to one decimal place. So don't fret if you're only off by 0.1%. However, if your calculations are a little bit more different to 100%, do double check your working out and make sure it's all good. Now, before we move on, let's quickly cover how to do a count percentage frequency conversion. If you want to convert a count to a percentage, divide the count number of the relevant interval to the total count for the numerical variable and multiply it by 100. If you want to convert a percentage to a count, divide the interval percentage value by 100 and then multiply it by the total count for the numerical variable. Whilst frequency tables are quick and easy to create, they can become messy and hard to interpret. To make numerical data more visually appealing and therefore easier to analyse, we often turn to the cousin of the bar chart known as the histogram. There are a few key rules to understand when drawing any histogram. The first is that the x-axis or the horizontal axis is the number line with markers for the starting and ending values of each interval. The second is that the y-axis or vertical axis indicates the frequency either in count or percentage for each interval. It should be labelled frequency or percentage accordingly. And finally, there is 1 bar per interval and the bars must be touching. This is to indicate that the intervals are created on a continuous number line. The bars are drawn in between the markers given the boundaries for each interval. Histograms make it quick and easy to see which interval contains more or less data points, given the relative heights of each of the bars. For example, we can clearly see that more football players kicked between 20 to 25 goals in the season than those who kicked 10 to 15. This was a pretty good footy side. As with frequency tables, you will often be asked to provide an answer as a count when the histogram displays a percentage frequency, or vice versa. Ensure you know what frequency type is used on the y-axis, then check what frequency type was asked of you in the question, and complete a frequency type conversion to the answer if it's required. Of course, you won't just be expected to draw histograms, but to analyse them. There are 4 key characteristics to histograms that give a good indication of the characteristics of the data collected. These are shape, outliers, centre, and spread. Let's go through how to analyse each of them now. So the first is shape, which refers to the distribution of the data, particularly with regards to where the peaks and tails are located. There are 3 main shapes to be aware of. Symmetrical distributions are, as the name implies, symmetrical, or mirrored around an invisible line that cuts through the centre of the data. Most people are aware of the bell-shaped distribution for its likeness to the shape of a bell. However, there are other forms of a symmetrical distribution that students often neglect to appreciate as symmetrical. For example, this bimodal distribution for marks on a test has 2 peaks and is still symmetrical around the dotted orange line. Note that its name bimodal not only means that there are 2 peaks, but both peaks are the same frequency, and hence 2 intervals serve as the mode. Likewise, this relatively flat distribution is also symmetrical around the dotted red line. The second shape is positively skewed, and positively skewed distributions have a large number of data points clustered on the left side, pushing the peak to the left side, and a long tail extending out to the right side. It is this tail that makes the data positively skewed. There are a few data points that are much bigger or more positive than the rest of the data points. A good example of typically positively skewed data is years of education, as shown here. Whilst most persons graduate after 13 years with a high school education, fewer persons will go on to university, and a very small number of persons will complete the 20 or more years needed to graduate with a PhD. Negatively skewed distributions are the third type of shapes and have a large number of data points clustered on the right side. This pushes the peak to the right side, whilst having a long tail extending out to the left side. Therefore, there are a few data points that are much smaller or more negative than the rest of the data points. A good example of typically negatively skewed data, as shown in this histogram, is 100-metre running times. Whilst most persons will run quite a slow time, few elite athletes can complete 100 metres in lightning fast time. The second notable characteristic of histograms are outliers, which is related to shape. These refer to intervals that have some data values in them, but are located some distance away from the rest of the data points. They are easy to spot as there is at least one empty interval between the outlier interval and the rest of the histogram. Here, our potential outlier falls within the 26 to 28 years of education interval. Just because a value is an outlier though, it does not mean it is ignored. It is still a valid data value, just an unusual one. You should therefore involve it in all observations and analysis, including the range. At the same token, don't let an outlier dictate the shape of a numerical distribution. Often symmetrical distributions look a little more skewed when looking at an outlier. Measures of center are the third analyzable characteristics of histograms. Two of the three measures of center can be read off a histogram, the mode and the median. The mode refers to the most frequently occurring interval. Hence, the mode is the interval with the highest bar. Here, our modal interval is the 17 to 18 seconds interval, indicated in yellow. The median refers to the middle value if all the data values were ordered from smallest to largest. Whilst this is easy to do by eye with a small number of data values, it's a lot harder with a larger number of data points, and almost impossible by eye on a histogram. Luckily, there is a formula that can be applied to find the position of the median. Here's the rule here. We take the number of data values, add 1, and divide it all by 2. Now I stress that this only gives the position of the median, not the value. You will have to find the data value at this position to determine the median. To find the median position, you need to find the total number of data points and input this as n in the formula. To determine n, first look to the information provided in the question. Often the number of data points is given there. If not, add the count frequency of each interval bar. Once the median position is found using the formula, add up the frequencies of the bars again from left to right. Stop at the bar that passes the median position. The relevant interval for this bar is your median interval and contains the median data value. Let's try it on this histogram. Now, the total number of data points for this histogram hasn't been provided to us, so we'll have to work it out ourselves. If we add up the frequency of each of the bars, we figure out that there is 120 data points within the histogram. Now all we have to do is chuck this in the median position formula, and we can see that the median is located at 60.5. Now that means the median is in between the 60th and the 61st number. Now the last thing to do is to go through all the bars again from left to right and stop at the bar that passes 60.5. And we can see that happens at the 17 to 18 seconds interval bar. So that is our median interval right there. Now you might be wondering what to do if the y-axis is a percentage frequency. Well, going back to our definition of the median, as the middle number that splits the data into two equal halves, the median is always located at the cumulative percentage frequency of 50%. In this case, no formula is needed. Add the percentage frequencies from left until you find the bar that passes 50%. This is your median interval. Spread is our last category to analyse and refers to the distance that the data values cover along the x-axis. There are two types of spread, the range and the interquartile range, but we will just cover range in this video. The range can be simply calculated by subtracting the smallest value from the largest value. To calculate this in a histogram, subtract the lower boundary of the smallest interval from the upper boundary in the highest interval. In our example here, the range is calculated by subtracting 8 from 28, indicating a data range of 20. As mentioned before, do not forget to include the outlier intervals in this calculation. Now that we have an understanding of the theory, let's put our knowledge to the test. Here we have a pumpkin weighing competition, where the weights of all pumpkin entries were weighed to determine which was the heaviest. The weights are in kilograms and were recorded below. I'd encourage everyone to pause the video and have a go at each of the questions before hitting play again and checking your answers against mine. The first question asks us to sort the data into a frequency table with intervals of 5 kilograms. The first question asks us to sort the data into a frequency table with intervals of 5 kilograms. Now before we do that, you're probably wondering what that weird symbol is in the first column. What that's essentially telling us is that the range of each interval starts at the left number and goes up to all the numbers but not including the number on the right. So that first category would include all data values from 0 up to but not including 5. Now I've sorted it out all here and we can see that the majority of the data points are within that 10 to 25 range. The second question asked us what percentage of pumpkins were between 20 and 25 kilograms. Well, to calculate that, we're going to need to do a count to percentage conversion. And if we go back to our formula, we take a look at all the relevant categories. In this case, there's only one. We find their counts, add them up, divide them by the total number of data values that there are, and multiply it by 100. So we had 10 values in the 20 to 25 kilogram range. We divide that by the total of 40 and multiply that by 100. And that gives us an answer of 25%. So 25% of the pumpkins were between that 20 to 25 kilogram range. The third question asks us to draw a frequency histogram, and I've completed that on the right here. Now a few things to notice. The x-axis is our weights ranging from 0 to 40, given that this was the range of all the data values. On the x-axis is frequency. Now the question hasn't specified percentage, so we just assume that it's a count. Lastly, the bars are touching. Now make sure the bars are always touching when you draw a histogram. The fourth question asks us what is the skew of the data and what does this tell us about the weight of the pumpkin entries? Well, having a look at this is probably approximately symmetrical. You can see it's all centered around that 10 to 25 kilograms and there's a little bit to either side of that, but it's mostly around there. If we were to put a line between that 15 to 20 kilogram interval, we could see it'd be symmetrical. Now what this indicates is that most entries were around that 10 to 25 kilogram range. We can clearly see that here. There weren't many on either side of that. There was a couple that were above 25 and a couple below 10, but the majority are in that sort of middle area. The fifth question asks, are there any outliers, and if so, what's its weight? Well, we can see that there's this one data value in the 35 to 40 interval. And if we go back to our table, we can see that its weight is 35.4 kilograms. Now notice I've used the word potential extreme right outlier. I've used the word potential because I'm not 100% sure that that is an outlier. There is a mathematical way to determine it, which will be later in the course, but for now I'm just going to say it's a potential outlier. And I've said extreme right because it's to the right hand side of the graph. Question 6 says, what percentage of pumpkins were weighed at least 20 grams? Well, the first thing we need to do is take account of all of the categories above 20 kilograms. So we had 10 in that 20 to 25 kilogram range. We had 2 between the 25 to 30 kilogram range, and 1 in the 35 to 40 kilogram range. Now that's a total of 13 pumpkins greater than 20 kilos. If we go back to our count to percentage formula, we take that total, we divide that by the total of the whole numerical variable, and multiply it by 100. And we can see that 32.5% of the pumpkins were greater than 20 kilograms. And our last question asks, what is the median interval? Well, to calculate the median interval, the first thing we need to do is work out how many data values there are. And from before we calculated that there were 40 pumpkins. Now the second thing to do is to calculate the position. So we'll take our formula of n plus 1 over 2 and put 40 where n is, and we can see that the median is located at 20.5. The very last thing to do is to do a cumulative count of the frequencies from the left to the right on the graph itself until we pass that 20.5 number. And we can see that happens in the third interval there. So our median interval is 15 to 20 kilograms. Thank you so much for watching my video, guys. I hope you enjoyed it and took a few things out of it. Please don't forget to subscribe to our YouTube channel and check us out on Facebook, as well as looking through our other videos. That's all from Further 101.